How are you guys?
Good.
Just as a little heads up here, I did add two things into the content library. So the basic trig identities are in there. I just have the basic set, not the like angle, sum, and difference ones, because I don't see those within the lookings through of questions. I didn't see those as things that I've commonly seen. If I do end up starting to notice that as I continue kind of going through these old AP problems, we'll add those in. But as of right now, I don't think that's something that I would spend a lot of time worrying about. Also worth pointing out the unit circles on the second page. So if you haven't refreshed yourself on that, that's there as well. Again, their expectation is that you have the unit circle memorized. I know. Or at least memorized enough that you can generate values for sine, cosine, etc. with unit circle angles. And then I went and screen capped everything that was in a pink box in chapters 2 and 3, at least to this point through chapter 3. And I'll continue to kind of update that. Now, some of this stuff is redundant, or like you don't need all of it, but I wasn't being that discerning. I was just grabbing everything. But at least it's like, that saves you a little bit of hunting, at least, to get it all in one place before you can go through and be like, yeah, okay, I won't remember that, without like putting it down on a note card and really making sure I memorize it, kind of thing. But at least it's all in one place, right? Which is nice versus it's on one note thing instead of like, 20 book or like 100 book pages or whatever to hunt through. All right. Do you guys want to start with some questions? Blake?
Could you do number 55 on
3.3? 3.3, number 55. Okay.
I looked at that and I'm like, it's too late to start this one. Right? I was like,
All right, this one with the picture. All right, the figure shows a circular arc of length S and a chord of length D, both subtended by the central angle theta. Find the limit as theta approaches 0 of S over D. Okay. So I'm going to add in a couple of values here. So I'm going to observe that both of those sides of that triangle have length r, where r is the radius of that circle. So from trig, I remember that S is equal to r theta, assuming that theta is in radians. Woof, Mr. Kulik.
wait, what is this?
Well, that's the arc length formula from trigonometry.
Oh, yeah. Mm-hmm. Yep.
Okay, so S is equal to r theta. And then D, well, that's a side length in a triangle, but it's not necessarily a right triangle. So I'm going to use the law of cosines, where I know that D squared is equal to R squared plus R squared minus 2R times R cosine theta. Is that everybody okay there? Or really that D is just going to be the square root of all that stuff? So far, so good. All right, so I have an expression for D and R, and I like both of these because they're both in terms of R's and thetas. So they're both in terms of the same variable. So the limit then, as theta approaches 0 from the right, of R over theta over 2r, well, let's do better with that, huh? Notice that each of these contains a factor of r squared. You guys see that? So I can factor that r squared off and then do the square root to just that piece. So I'm going to have like r and then the square root of 2 minus 2 theta. Pretty good there. Okay. What else can we do with this now? So I got the r's out of there. We're just in terms of thetas. But if I go to 0, if I just do a direct substitution, I get 0 over 0, right? Which is no bueno. Well, there's not really a conjugate to use because it's just like a single thing. I don't think that's going to help me a whole lot. Let's think. There's got to be something else we can do here. Well, I mean, like we could evaluate this with a table, sure. Use the calculator. That's not unreasonable assumption to make. Let's go ahead and do that, I suppose. That's not an unreasonable suggestion. So I'm going to use x's for thetas. And maybe after I see what the answer is, we can have come up with some reasonable algebraic solution to that. So I'm going from the right, so I want positive values. So let's just kind of see. Yeah, it makes sense. Well, what does this look like it's heading towards? Looks like 1 to me. Yeah, anyone unconvinced of that? All right, let's see. How would have we gotten to that? All right, well, we know this is equal to 1. Let Mr. Kulik play with this for just a moment. Well, let's go look at what they did. Don't see anything clever that jumps up to mind, but
How many questions like this are going to be on our test?
like this one,
Yeah.
probably on the test I'm going to give you,
Yeah.
0.
Oh, cool. Okay.
Does that feel fair?
Yeah, I was a bit worried when you were having a little bit of trouble with it.
Well, it just,
Like, maybe that one might be a little bit too much for me.
well, no, it's like, okay, they did that, okay. Oh, that's an interesting choice. They did that. Okay. Interesting. Okay. Well, they went and did a different approach and used a different fact. They didn't use the law of cosines there to get their other piece, but nothing we did was incorrect on this. And to be quite honest with you, like, what they did was, I think, way sneakier even than what I was trying to do there. So just to show you what the textbook solution was, what they did is they went in, they made the angle bisector here. And since that's an isosceles triangle, that piece becomes d over 2. So we can say that like sine of theta over 2 is equal to opposite over hypotenuse. And then they rearrange that to get the r by itself, and then, then they used, they rearranged that to get the d by itself and substituted that into the thing, and that's what they used. But okay. I think that's way sneakier than what I was trying to do with the law of cosines. It's like, well, okay, there's an expression, it's got the right things in it, the r's canceled out, this is all looking nice. So if you did that, you'd have like, we got d is equal to 2r sine of theta over 2. And then if you do your limit, you have, what is it? Was it r over d or is it d over r? I now forget which one they put on. S over d, okay. So that gets me to theta over 2 sine of theta over 2. And then what they did is they wrote theta as 2 theta over 2. So that these guys could cancel. And then they did a change of variable. So let, x equal theta over 2. And this is one of the things we've seen before. If you went to our memorized list, that was a chapter 1 thing somewhere in here, I think. I like what we did better, to be honest with you. I have to look for it. But that's what they did. If that, you happy with that, Blake?
Yeah, I think I'm good with just doing the first thing and just graph.
Yeah, or doing a table or whatever.
Yeah,
like that's reasonable. It's good enough. Blake, do you have some more?
Are you able to answer questions on the AP practice?
Sure. Is it 15 or something?
No, I don't think so.
Okay, because
I haven't quite gotten 15 yet.
15, so I accidentally, I shouldn't have assigned that one because it's.
Oh, take a look at it right now.
You need to use the chain rule on it. After like we get through the 3-4 lecture, you'd be able to do 15, but
okay.
I don't think the answer for your 15 isn't going to match up with like if you did it on the calculator.
Okay.
The answer you'd get from the calculator, so like something should be up, but it's because you don't know how to do that particular derivative yet.
Okay. So
I'm not going to tell you what the answer is. I'm just going to tell you that like just hold off for a minute.
Should I learn how to do what's it called, the scat? What'd you call it?
The chain rule?
The chain rule.
That's what we're doing.
So I should learn that.
We're doing that in the next, like in what we'd be doing today if we had a full day of class.
Okay.
We'd be doing it today.
Oh, so this isn't
do Sunday then?
Well, we'll do enough to do the chain rule. It'll take me like 15 minutes to show you how to do it initially, enough to be able to do 15. But the issue is this e to the negative x rather than just e to the x. That's what's throwing that. I mean, that is what's telling you need to use the chain rule for that.
So
which one?
I don't think you're able to give me the answer, but for number 6, could you like? I don't know what I'm doing with it.
I would just do the binomial expansion and then simplify.
Yeah.
And it's going to be kind of sucky, but
yeah, I was able to get an answer, and I thought that the answer was right, but it's not one of them.
Okay.
So clearly it's not. But
let's do this real quick.
Maybe you know something they don't like.
I do know something that they.
All the capitals.
That's very true.
Come on, that's a good one, guys. Call back to last year. All right, so I would start with my binomial expansion. So I'd have 8 plus 4h plus 2h squared plus h cubed, and then 4 plus 2h minus 8 minus 4 all over h. Those guys are all going to cancel out. And then I can reduce an h. So I'm going to have 4 plus 2, so that's 6. And then I have a plus 2h and an h squared. Oops, forgot my limit. And so that just turns into 6 when I do my direct substitution. That looks like what I would pick.
Yeah. So I see what I did wrong, and it was.
Did you distribute exponents?
No, I don't know how I got the numbers that I got. I'm looking at it now. I think I just didn't add everything. So that's on me.
Okay. Oh, that's not right though, is it? Oh,
I graphed it and I did not get 6.
Yeah, here. This is.
I got non-existent.
That should be 12, and that one should be 6, which.
Crazy. You're insane.
No way. All right.
So that should be. There we go. Sorry. I forgot the coefficients.
Wait. How's that? I gotta write this all
Uh,
12 plus 2.
oh,
No, it's
sorry.
here. Oh.
Yeah, sorry. I put that's supposed to be 14 there. So 12 plus 2 is 14. So like the binomial expansion for this is this.
And then it's gotta be
So 3 times 2 squared is 12. 3 times 2 is 6. So that's why I goofed that up. I forgot the coefficients on my binomial expansion. And of course, one of the multiple choice answers is exactly if you make those kinds of mistakes. Of course, they're doing that.
Yeah, I don't know how I did the math wrong, but somehow I did the expansion just completely wrong.
Oh,
Just
okay.
fully wrong numbers.
Okay.
So
Well, that should make you feel a little better. That it's like, yeah, I knew what to do. I just didn't do it right.
yeah, exactly.
That's a good first step, at least, like to know that, okay, what I was planning on doing was the right thing to do. I just need to do a better job at doing it next time. Okay. And when you look at it, it's like, yeah, that's what I should have done. I don't know what I did instead. But sure. Others. Teagues?
Can you do 17 and 3.2, please?
3.2, you say?
Yes, please.
Okay. Let's see. 3.2. And you said 17?
Yes, please.
Okay. Oops. Insert. Oh boy, that couldn't be any smaller there, could it? All right. So, the first thing that I would do is, I mean, this is a product rule problem, right? So,
I was just saying, do you have to do the product rule of that P root P too?
no, I would call that P to the 3 over 2,
Oh.
right? Because I P to the first times P to the 1/2.
Yeah, right.
So let's do that so you don't have a double product rule. You could do it as a double product, but like, please, let's not.
Wait, if you were to do it as a double product rule, would you just find the derivative of P times P and then add it to the derivative of P and then do the product rule of that?
So you'd have like a product rule inside of another product rule if you're doing that. So like I still have e to the p, then I'd have to the first, and then plus inside here would be my other product rule, and then I would keep on going.
Okay.
Hi, I have the bishop with me.
Okay, come on in. Good morning, Bishop Cepeda.
Hello.
How are you doing?
I'm doing great.
Great.
I'm moving into calculus here, right? Is that
Yes.
what it is? I was never good. No calculus. So you tell me, this is my class. I'm like, oh my, look at that. It's very fun. I have no words.
That's why we use all symbols, right?
Exactly. That's great. We are good at that, especially in the Catholic Church, right?
Yeah.
We are very good at that.
We go to mosque. Yeah.
It's really enjoying this tour. I have my tour guides all over here. But just wanted to make good stuff. I'm sure you have no questions for me, right? Sure. Thank you. I don't have any questions.
That's okay. Yeah.
Again, I'm speechless.
You answer to a higher power anyway, so I don't know what kind of answers I could give you.
I like that. Okay. Let's see you.
I'll be walking the line.
The simplest joke.
What? Come on.
No, you're right.
You got to know your audience, right? If we're going to make some jokes, let's do it. All right. So Luke, you had asked about if I wanted to do this as another product rule in there, like it would go your product rule, your other product rule would go in there. But Lord help us, let's not do that, right? Just do it that way. Much easier. And then over here, well, that's, I don't know why square root of 2 would be in there. And then still just derivative e to p is just e to p. And, oops, this should be dy dp though, right? Huh? And then we're basically done. So I just go do some distributing. Maybe I'll factor the e to the p out, and that'll save me a little bit of hassle. But nothing really to simplify in there. I think that's good. Teagues, if you wrote that for me, I'd give you full credit on that. It's a fine final answer. You need to put it all back into radicals or anything. I think that's good enough for me.
Okay.
Yeah. Paul, in general, what I tell you is if the calculus is done, And on the AP exam, like on a free response question, if the calculus is done, then so are you. Like, don't waste your time trying to like make the algebraic expression as pretty as possible. Unless it's like, show that this derivative is equal to this, in which case you know when you're done because you need to get to what it's supposed to equal. But if it's just like differentiate this, doesn't matter how ugly it is, it's fine. Right? It's just done when the calculus is done. So like even back here, I think that expression would even be okay.
I was gonna say, yes, or that.
Yeah, on the AP exam, yeah, that would be fine. I would like maybe a little bit more than that, since there's not like, we're just talking about like doing some light multiplication, maybe regrouping some terms. But, you know, I'm not gonna be crazy about like giving me the simplest expression, because sometimes that's way harder than the calculus pieces to like dig this thing out into something that looks nice. And in those kind of problems, that I would, not that I even would do this on your test, but if I were to do it, I would say like show, the directions would show, and then it would be like this thing is equal to this. So you know exactly what the end has to be. Otherwise, I would say like you're done when the calculus is done and like light simplification is over. And I'd be happy to answer, like, is this enough? You know, I'd be happy to answer that kind of question. Because I don't want you to spend 5 minutes like trying to simplify something that's horrific.
Yeah.
You know? Especially when it's not something that's not the expectation either on the AP exam. So, Teagues, you feel good about that though?
Yeah, that's good.
And again, like this observation here is a huge time saver, right?
Right.
Like that simplifies the problem enormously
Yeah.
if you're able to avoid having to do that.
I did the product rule for that too, and that's why I got confused.
Yeah, it gets big really quickly. And that particular skill of looking at this and seeing that, okay, there's two product rules here, but I can really just make it one product rule. That's the at this level, that's the necessary skill to get good at this. Is if you can take a problem that could be really difficult and make it a heck of a lot easier by peeling a layer off of it like that, just doing algebra, that's enormously helpful. So just kind of getting used to looking for that before you dive in. Is at first glance, it's very tempting to just be like, okay, double product rule, here we go. And miss that really nice shortcut there. Anybody else?
So for 37 for 3.3, I think they asked for the rate at which like the ladder fell.
Yeah, so they're asking for like dx d theta is what they're asking for on that problem. We did this in the previous period, and I'm going to run out of time to do the chain rule piece that I was expecting to do, and that's fine. So let me do this, talk about this problem here briefly, and then I'm going to do like 1 second on chain rule to give you guys an idea of like what's going on, and then we'll pick up the rest next week. It's fine. So we have like this ladder, 10 feet here. We have the angle between the ladder and the wall. We're told this side is x, and it's looking at how fast does x change with respect to theta. So what we're asking for is dx d theta. So if I look at this drawing, I see a way to relate the theta, the x, and the 10 together. So sine theta is equal to opposite over hypotenuse. Everybody cool there? I'll take the derivative then with respect to theta for both sides. Since I want dx d theta, I'm looking at the rate of change with respect to theta. Cool there? The derivative of sine is cosine. I'm sorry, negative cosine. No, cosine. And the derivative of x over 10 is 1 over 10, right? Almost. So here's a big important observation. The derivative with respect to is the same variable over here, but it's not the same over here. You guys see that? We're differentiating a variable x with respect to theta. That changes things a little bit. We need one more additional factor here. We need a dx d theta. If I over here, I would have, by the same reasoning, I'd have a d theta, which is why we never write it. When the variable with respect is the same as the variable you're differentiating, you get no other like differential pieces like that. But if the variable is different, you get like that extra differential piece there, which is what we needed though, because this is what we're asked to solve for. So I just multiply both sides by 10. And then I plug in my pi over 3, which is what the question called for. And that cosine of pi over 3 is 1/2. And then this is the rate. The x is measured in feet, and the angle is measured in radians. So that rate would be 5 feet per radian. Is the rate in which that distance from the bottom of the ladder to the base of the wall is changing as that ladder like slips down. Okay. 2-second chain rule. We'll do a whole lot more exampling and stuff on was it Monday? But I wanted to at least like touch on this just ever so briefly. So what the chain rule is used for is if I have a composition of two functions. So let's say I have a composite function. I'm going to call that cap f. So if cap f is equal to f of g of x, then the derivative of cap f is the derivative of the outside function, where the inside function stays the same, times the derivative of the inside function. So that is our rule on how to do the derivative of a composite function. That's our chain rule. So for example, if I have, say, f of x equals the square root of x squared plus 1, my outer function you should see as the square root of x, and my inner function as x squared plus 1. So if I take the derivative of the outer, that would be 1/2 x to the negative 1/2. The derivative of the inner would be 2x. Is everybody okay there? So if I do f prime of g of x times g prime, I'm going to have 1/2, and then in place of the x in my f inverse, I'm going to write g of x. So the way to think about this is just the derivative of the outer times the derivative of the inner. Right? The inner function remained the same when I took the derivative of the outer, and then I just multiply the derivative of the inner function afterwards. We'll do a bunch more examples on this next time. But that's enough to be able to do that problem 15 that I accidentally put in there where I thought I was real careful and didn't have any chain rules in there, and then somebody asked me about it fifth hour, and I was like, shoot, there is one chain rule in here, and it's like the most trivial of chain rules, but like, gotta have the chain rule to do it.
Could you grab that?
You're welcome. You too. Take care.